Hello everyone, my name is SKTU2153-02 and we are from Group 1. Welcome to video presentation for the mechanics of metro class. Today we are going to show you a very interesting project. We have to build a solid bar using a very simple material, uncooked spaghetti. Because we are Group 1, we made the bar with a square shape. The rule is simple. The spaghetti bar must be 30 centimeters long and 1.5 centimeters thick. Later in this video, we will also show you the molder we use to shape this material. So, what's the objective of this project? First, we want to test how strong this spaghetti bar is. We will do a bending test by hanging water bottle from the bar. We will slowly add more water to increase the load until the bar finally breaks. Second, after the bar breaks, we will calculate the allowable normal stress. For this project, we will use safety factor of 1.5. And finally, we will show you our calculation steps to create the shear force and bending moment diagram for the load we tested. Alright, we move to the next section.
I just had to let you know you're
Hey, okay.
Cakap Ustaz.
Hello everyone, I'm Deng Zian. So I will bring you guys to go through the calculation part for our group project as shown in the cell of our first page. So we have a simply supported square bar spanning 30 cm with a cross section of 1.5 cm by 1.5 cm. Then there's a point load P representing a water bottle hangs exactly at the center, which is 50 cm from this support. So during our test, we find out that the bar ultimately broke when the water volume reached 1.5 liter. So by assuming the mass of the bottle is negligible, since the value is too small, so we try to convert the volume of water into the force load. So by using the standard water density of 1000 kg per meter cube, and the gravitational acceleration of 9.81 meter per second squared. So we will try to find out the mass of water used by multiplying the density of water with the volume of water used. So lastly, we will find out the mass of water is 1.5 kilogram. Then we try to get the value of the force of the water exerted on the beam. So it's still same by multiplying the mass of water with the gravitational acceleration value. We will find out that the force exerted by the water to the beam is 14.715 Newton. Next, we try to solve the radiation force at the supports by using static equilibrium equation. By taking the summation of moment about point A, we will find out that the outward radiation force at support B, FB, is 7.3575 Newton. Because the system is perfectly symmetric, so by checking our vertical forces, we will confirm that the radiation force at support A, FA, is also exactly 7.3575 Newton upwards direction. To build our structural diagrams, we try to analyze the beam in sections. So firstly, look at the first half of the beam from s equals to 0 to s equals to 0.15 meter. We try to use the method of section to solve the calculation part. So firstly, we will find out that the internal shear force V1 is constant value, which is 7.3575 Newton. Meanwhile, the internal bending moment will get a equation which is 7.3575x Newton meter. So which means initially when f equals to 0, the moment is 0 Newton meter, and it will climb out until 1.103625 Newton meter when it is at the midpoint of the beam. So moving on to the second pages. So we try to evaluate the second half part of the beam between 0.15 meter to 0.3 meter. Now we have passed the central hanging load. Our shear force drops and change signs to negative 7.3575 Newton. And setting out our moment equation, we will find out that this section will produce a negative 7.3575x plus 2.20725 Newton meter. So plugging in our boundary value, the moment successfully transitions from 1.103625 Newton meter at the center back to 0 at the right support. So plotting this value will give us clear visual diagrams. The shear force diagram is a step function, shifting abruptly from positive to negative at the center point where the motor hangs. So here is the bending moment diagram. It creates a distinct triangular shape peaking at the dead center with a maximum bending moment of 1.103625 Newton meter. So finally, let's look at the material performance calculation shown on the lower right part over here. So firstly, we calculate the geometry properties of the square bar. The distance from the neutral axis to the outer edge is half of the height. So it will give a value of 0.0075 meter. So the area moment of inertia is calculated by using 1/12 BH cubed. So lastly, we will get a value of 4.21875 times 10 power negative 9 meter power 4. So by using the formula, the pressure equals to moment sigma equals to mc over I. We will determine that the maximum bending stress experienced by the bar at failure is 1.962 MPa. So If the safety factor is 1.5, we will try to divide the sigma mass with the 1.5 to get the allowable design stress, which means the stress applied is safe for the beam as it will not break when the stress is applied to the beam. So we will get a value of 1.308 MPa when the safety factor is 1.5.
So now we have come to the end. To conclude everything we have done, this project really helped us see how the theory we learned in the mechanics of materials subject actually applies in real life. By designing and testing the spaghetti bar, we could understand better how things like shape and material affect the strength of a structure. When we tested it, we gradually added load until it failed, and that part really helped us visualize how bending and stress actually happen, not just on paper. It also made it easier for us to relate our calculations to the real results, especially when estimating the allowable stress with a safety factor. Overall, it was a good hands-on experience. We not only understood the concept better, but also we improved our teamwork and problem-solving skills. Honestly, it made the whole topic feel more real and easier to understand. Well, that's all from us, and hope to see you guys again.